Ocean currents contain a massive, untapped reserve of kinetic energy. Unlike erratic weather systems, this volume of water moves with a relentless, mechanical rhythm. Extracting that energy requires a specific form of hydropower called tidal power, which converts the natural ebb and flow of tides directly into electricity. This chart illustrates the advantage of tides. On the left, erratic line graphs represent unpredictable wind and solar. On the right, tidal power mounts onto a constant sine wave. Historically, a rigid cost barrier limited development to a few sites, making extraction highly expensive. Recent iterations in turbine engineering have lowered that threshold, drastically expanding the number of coastal locations where extraction is economically viable. These new subsea networks are now positioned to become a foundational energy source for Britain. Anchoring a national grid to geographically fixed, highly predictable ocean currents removes the volatility of weather, stabilizing a nation's baseline energy security. The mechanics of capturing ocean currents differ sharply from wind because of fluid density. Water is hundreds of times denser than air. We can see how this density dictates engineering by looking at a standard onshore wind turbine. A marine turbine requires a fraction of that mechanical footprint. When placed side by side, the marine blade is exactly 1/3 the size of the wind generator. Despite that smaller profile, the marine unit generates 3 times the electrical output of its counterpart. In physical terms, these new marine blades span approximately 20 meters in diameter. To safely accommodate a 20-meter rotation beneath the surface, the hardware must be submerged in water depths of around 30 meters. Because the surrounding ocean fluid is so dense, these blades extract that massive force while rotating relatively slowly. This deliberately sluggish rotation minimizes the risk to fish and marine ecosystems. The high kinetic density of the ocean allows developers to extract massive electrical yields using a much smaller, less physically intrusive mechanical structure. Operating heavy machinery 30 meters underwater introduces severe structural challenges. The primary threat to the longevity of these blades is a fluid dynamics issue called cavitation. This animation illustrates the physics of cavitation. As the blade cuts through the water, it creates a localized zone of extremely low pressure directly behind the trailing edge, causing the water to boil instantly and form localized air bubbles. When those bubbles exit the low-pressure zone, they collapse violently. The resulting implosion sends shock waves directly into the metal, causing intense vibration and severe structural damage over time. Engineers must also account for submerged physical debris that drifts unpredictably into the path of the rotating array. To survive the corrosive saltwater chemistry, developers are utilizing robust anti-corrosion materials adapted directly from existing North Sea oil platforms. Research divisions like the Sustainable Energy Group at the University of Southampton are actively testing multiple blade profiles to mitigate these precise stressors. Designing subsea generation networks is an ongoing challenge of material science, keeping complex machinery alive in a highly corrosive, pressurized environment. Scaling this hardware from isolated tests to national deployment relies entirely on the topographical shape of the coast. European Union research mapping has identified over 100 viable tidal sites. 80% of those are concentrated directly around the coastlines of Britain. The most lucrative locations share specific geography, waters funneled between islands or along heavily indented coastlines that force water into accelerated currents. The initial testing station for this deployment was targeted off Lynmouth in Devon. Moving to full-scale infrastructure, developers mapped a massive bottleneck between Orkney and mainland Scotland, known as the Pentland Firth site. This single geographical pinch point forces enough kinetic flow to produce 10% of the entire country's electrical supply. Further south in the Channel Islands, the currents around Alderney provide an even denser deployment zone. To benchmark the output of the Alderney site, we look to Britain's largest existing baseline generator, the Sizewell B nuclear plant in Suffolk. A single undersea turbine farm mapped for the Alderney site is projected to generate 3 times the 1,200 megawatt capacity of that nuclear facility. This yields far more electricity than the Channel Islands require. The surplus would be fed into the French grid and then routed back into mainland Britain via cross-channel cables. Additional high-yield arrays have been identified for the Bristol Channel and the straits between Campbelltown and Northern Ireland. By targeting these natural topographical bottlenecks, research identifies sites capable of producing more than 1/6 of the UK's total power, allowing isolated coastal arrays to surpass the output of the country's largest nuclear stations. All of this offshore generation still requires a physical connection to the mainland consumer. Each marine turbine mounts to a vertical tower anchored to the seabed. Electricity travels down the structure to the national grid via underwater cables. The tower's top protrudes, housing beacons to safely route shipping and allowing engineers to lift the mechanism out for maintenance. The economics of this infrastructure have stabilized. Electricity generated from tidal sites is now priced competitively with modern gas turbines. By leveraging established North Sea manufacturing techniques and more efficient blade designs, these arrays are projected to undercut the costs of a nuclear industry, currently struggling with aging infrastructure and high overheads. The ultimate goal for the national grid involves developing tide, wind, and wave power simultaneously as a single interconnected system. Fully developing this domestic technology allows the UK to begin closing fossil fuel and nuclear plants. By mastering these specific high-velocity fluid dynamics, Britain creates a specialized export for other island nations, like Japan and New Zealand, that share similar coastal geographies. Mastering the physics of ocean currents transitions the United Kingdom from a grid dependent on imported fossil fuels into a self-sufficient exporter of advanced renewable technology. This video is brought to you by the IELTS FOCUS 0847705973, an English center specializing in IELTS preparation.